Hello, everyone, and welcome to Handmade Hero. Sure, we've code a complete game live on stream. We are kind of at a little bit of crossroads today. Let me go ahead and run the game for you so I can explain what our situation is. While John blissfully plays Manifold Garden, we have to deal with our own sort of garden of troubles here. So basically, if you look at where we are with lighting, which is what we're sort of grappling with at the moment, here's a fresh build, and here's the game running. So what we sort of did is stuff the lighting with just a generic sphere right now, and you can see that we have two sort of things that we now want to move on to. We have lighting sampling in there, and it's pretty good. Like, I'm not horrified by it, but it's not great. And the reason I say that is because you can see the voxelization artifacts that you get from just straight trilinear sampling of your light, which is what's happening here. So you can see in the interior, it's harder to see, and that's because I think there's it's less obvious because it's more subtle. It's still there, right? It's still there. I can see the artifact now that I know that I'm looking for it. I can see it in the interior, right? But where you can really see it is anywhere there's a harsher light transition. So you can see here where we've got the fall off of the light. And you can kind of see how that's, just around those edges. You can see those really ugly, blocky, sort of traditional bilinear artifacts you'd see. They're trilinear in this case, but you're more familiar with them, and I'm more familiar with them as bilinear artifacts because we see them much more often in that context. Trilinear, voxel sampling is not a thing that we do that often by comparison to bilinear, which is done everywhere. So what we can see here is that our sampling isn't awful. It does work, but it's not great. And so one thing that we probably have to keep on our radar if we don't do it right now is to make this better. Like, we're going to need a better scheme, I think, unless we just want to accept it that, hey, it's an indie game, so it's maybe not as awesome as it could be if we had a dedicated graphics team who will solve this problem, right? But that's usually a poor excuse, so we may want to go try and improve it ourselves. However, that said, what we can say about it is there's really only one specific artifact that we're seeing right now, and we kind of know what it is. So it's entirely possible that we could just accept that artifact temporarily and move on to the actual lighting transport part, get that working since that's a separate part of the puzzle, and then from there we move on to trying to fix the sampling. All of that is certainly possible. I just don't know, again, because I'm not sure, I just don't know how important that particular part of it is. So my guess is we should just move on to the light sampling for now. I'm sorry, not light sampling. We should move on to the light transport for now, since we have to kind of bring that code up to speed. So I think we kind of want to do that, and then from there we can go ahead and assess afterwards what we want to do to try and improve the sampling of the light information we do have from there, right? And we can see that even with the artifacts, it at least still is pretty cool the way we can sample these lights. And so once we get some actual transport in there, where we're going to have some more interesting things happening, like shadowing and stuff like that, so that, you wouldn't see light kind of in this quarter and stuff like that, it seems like it would be probably a pretty cool aesthetic as well. And, we'd have a number of different lighting environments as well. Obviously, this one just has a light hovering above the character. But, we'd want lots of things like, our lamps specifically to be on and shining light and things like that. So, I think it would create a nice lighting environment. And so the question will just be, how bad is this sampling? And is there anything we can do that doesn't tank the frame rate that would be usable, right? So that's where we're at. And with that in mind, I want to just make a judgment call here and say, let's do the lighting sampling. And the reason I want to go that route too is because one of the things about the lighting sampling that's worth noting is the light sampling itself. We're going to want to work on that algorithm for a little while, and as we work on that algorithm, we may also discover some things about the way we're working with light that change or inform how we might sample it. So it's possible that by ping-ponging back and forth between these two sides of the problem, maybe we'll gain insight into the other side while working on one of the, side A, the sampling. Maybe we'll gain insight into the sampling side while working on the transport side, and maybe we'll gain from the transport side while working on the sampling side. So ping-ponging back and forth between them maybe makes some sense, as opposed to trying to get one perfect and then moving to the other one, because for all we know, they may be a little bit more intimately connected, because again, the transport side does have to itself sample lighting. The sampling side has to reconstruct lighting, which is what comes from the transport. And so that interplay there is, it's a process of gaining that understanding that we're trying to do here. And so what we want to kind of work towards is getting both of those problems solved together, as opposed to them being completely, it's not like they're these disparate problems that bear no relationship to each other, right? And so if I go ahead and pop over to the lighting transport side of things, and we start to think about, well, what are we going to do to make this stuff work, right? What you can see, what we've got here is a begin and end lighting computation call, and basically all that happens is the begin lighting computation enables the lighting. What I probably want to do when we end is disable the lighting, but I don't know that we actually have such a thing at the moment. How does that actually work? We should probably have it turn off. You can see the enable lighting here. I don't know that there's a disable lighting, so that's what we should probably do. It's not important right now, but something to think about. But basically, as you can see here, all begin lighting computation does is say, look, start tracking lighting through the system. That's all it does. And so when you go to render, you say begin lighting before you put down all the scene stuff. And then the idea is afterwards, when you call end lighting computation, after that, eventually we'll have a thing where we don't do any lighting on anything after it. That's so that you can avoid doing lighting on things like the title screen, like the thing that's stamped over the title screen, or the debug HUD or whatever, right? So we don't always want lighting. Most of the time we are lighting, but sometimes we don't want to, and that's the important part there. So, moving on from that, we have begin lighting computation, and then we have end lighting computation. End lighting computation is actually that does all the work, because only by the time we've gotten to the end of where we want to do our lighting computation do we have all the information. In between these two calls, the exterior code has done all of the specification. Where are the light sources? Where are the occluders? That's basically what needs to be happening, right? And so as we move through this set of stuff, what you can see here is we have this old sample table we were working on. All of this stuff we kind of replaced, because what we did is we made a generator that generates well-distributed sample spheres, and you can see that here. At some point, and that point is probably going to be very shortly, you can see that there's a table of zeros here. You may be wondering what that is. And the answer is, eventually what we're going to be doing is saying how to weight these samples when we cast rays, how to weight these samples into which sides of the spheres and so on. And we don't actually know if that's something we want to do yet. So what we may want to do is just say each individual ray just goes to one side, whichever side it left through. So there would be no blending, right? And so eventually we may say, look, the way this actually works is actually just it looks like this, right? And so we don't really know exactly what we want to do there, but we're going to work that out now. But the important part is we already figured out how to do a well-distributed sampling on the sphere, and that is actually, you can see it hovering right here, right? We debug drew it just to make sure it has good coverage. You can see we have a really nicely distributed set of points there. Again, not white noise. This is blue noise here, or at least blue noise adjacent. And so we have, the first step of that problem sort of sorted, but there's more to it left. There's more to come, basically. And so we'll be taking a look at that as we go. So inside end lighting computation, now let's just go through really quickly what we're going to be trying to accomplish here. So what you can see in end lighting computation, this sample table stuff we're not going to need anymore because I believe this stuff is just kind of a holdover from when we were kind of screwing around with how we're going to do this lighting. So the sample table stuff, which is here, right? I don't actually think we want that anymore, right? These things are, I don't even know what this stuff. What were we doing here? Let's take a look. I think this stuff is just garbage now. Yeah, so you can see this stuff is just we don't need this anymore, right? It's not actually being used. It can go away, right? I think that was before we had gone down the sampling sphere route. So I think we're good. Yeah, it's all clean. So when you take a look at end lighting computation, there's some debug code in here, but then basically the first thing that happens is what you would expect. This code is test code in there to see what happens if you accumulate the lighting over time. We probably want to re-enable that testing as well, because it's a good way to test to see that the light transport is unbiased, which we probably want it to be, at least to a certain extent. What you can see here is we've if-zeroed out the part that actually does any work, and that's because we weren't actually doing the lighting transport anymore. But then what we did is we have the code at the back end that's going to be responsible for outputting the actual information about what the graphics card needs to sample. And if you take a look, we just have a ton of code stuck in here that's mostly all for debugging, right? This right here is the thing that stuffs our voxel with fake values. This stuffs our voxel with that orb that you saw there. So that's basically the code that's producing this fake light. This is not light transport. It's just a sphere of light that we, basically a distance fall off light, just stuffed in there. That's why it doesn't do any shadowing. It's not doing any transport, just stuffing the light into the voxel directly. And so what we want to do now is start to move this function towards something that's actually going to produce some kind of lighting we can use. And so the first thing I would like to do is take one step forward, and that's probably what we'll do today. The step I'd like to take is figuring out how we're going to go from light probes to voxels, right? Because right now, what we're actually doing, like I just said, we've got this thing at the end here. Right now, what we're actually doing is directly stuffing light into voxels, right? These voxels themselves are the things that are actually storing the light here. The light probes are not, right? So we're not touching light probe information. We're not even building light probe information. All we're doing, the entirety of the process, is literally just us doing these voxel stuffs directly into the lookup structure that the GPU actually uses for lighting. And whether or not we want to do that long term, we don't know. But what we do know is that at the very least, if we want to actually have light probes that we place throughout the world where we think they make the most sense, we're going to have to start with those and then move to voxels. And if in the end we choose to remove the voxels and have the GPU work with the light probes directly, that's fine, but we still need to take the step of at least having the light probes be the thing that is persistent, right? So I'd like to start with that step. And furthermore, we probably also want to start to think about how we're doing actual lights. So right now, we don't really have any idea of what a light is. We may want to have lights be a first-class citizen. No particular limit on them, just a way of saying this is a light. Because right now, what happens is we actually do warrant to the renderer that there is a light. Here is the call. But the light, instead, is just a cube, right? But I think that's a bad idea because since we are saying that the game will announce where the lights are, even if there's 100 of them, it's going to tell us where they are specifically. It's not going to bury that information into some kind of hard-to-detect scenario. Since it is going to tell us where the lights are, and generally speaking, that is what we want anyway, like we know what's supposed to light up in the game and what's not, we probably want to then take that light information and give it to the renderer so that it can bias the sampling towards hitting light sources, right? Not biased in the sense of creating a biased renderer, but biased in the sense that when it does importance-based sampling, it can know that it should try to aim for light sources, right? The word bias is difficult because there's a very specific definition of bias when it comes to talking about the output of a renderer that doesn't like, so for example, let's suppose that we know that our renderer will go out of its way to try to see if it can hit light sources when it does its raycasts, rather than using a perfectly even distribution of outgoing rays. You would obviously call that biased sampling, right? I mean, that's a, intuitively that's a phrase you would use to describe it, because it is biased towards trying to hit a light source, right? It obviously is not a uniform distribution. It's not even a cosine weighted distribution. It's very specifically a distribution weighted towards trying to hit the light source, right? However, there are plenty of examples of sampling schemes people have constructed, pretty much all the ones used in production as far as I know, that are biased in exactly that kind of way. The trick is, as long as you create the correct probability model on the back end, biasing your sampling doesn't mean your rendering ends up being biased. And what biased means in a renderer means over time, as you average the results of a subsequent rays, biased or unbiased, biased means you will converge to the wrong answer, unbiased means you will converge to the right answer. So a biased renderer, if you run it forever and just keep accumulating results, a biased renderer will converge towards an erroneous answer, usually infinitely bright or infinitely dark, I would assume. But I guess that's not necessarily true. Whereas an unbiased answer will return the correct answer if you ran it infinitely long. That's the actual difference between the two. And so the crucial thing you need to know is when you are biasing the sampling, you need to know that you're biasing the sampling, and you need to account for that in how you combine those samples. But that's really all there is to that, and hopefully that makes some sense. Anyway, so we probably want this information to come through, and that's something that we should look at now as well. So those are the things that I want to do. Start getting the light probes involved directly in here, get them through to the voxels, and we probably also want to start tracking those light sources so that we understand where the light sources are supposed to be when it comes to lighting time. At the very least, we're going to need that because we know they have to inject light into the system, whereas nothing else does. And so if we don't understand where a light source is, we're not going to be able to put light in the system at all, and everything will just be dark. So here we are in the end lighting computation. As we move through here, the first thing we're going to want to do is probably ignore these guys, continue to keep them out, because what we want to do is just build the light probe set and then output it. The spatial partition is not for the probes. The spatial partition is going to be for the boxes, I believe. So let me see here. Is that correct? Yeah. The spatial partition is just for doing the raycasting. So that's just taking the basically the occluders and building a hierarchy so that they can be raycasted more quickly. So we're basically looking at sort of the part that comes below here. Now, as we're looking towards this, these boxes here, where we're looking at these box store directions and accumulation and all that stuff, we really don't want this stuff anymore. So more what we need to look at here is how we're going to combine the light probe arrays. So I'm going to go ahead and move this down because this is basically, a non-issue for us now. So I'm going to go ahead and move this down and kind of get it out of our way. Because this is not really relevant anymore and will eventually go away, but we may want to look at how we were doing our averaging over time there. So we'll leave it there just in case we want it for reference later, so we don't have to go dig it out of GitHub or something. Here we've got how we were drawing some of our sample points here. We don't really need that at the moment either, but it's just some debug stuff for drawing. So I'm going to move that out of the way as well. Let's get this down here. And this is what we're currently doing to draw our sampling sphere. Again, not super concerned about that at the moment, so we're going to move that down here too. We're just going to leave all this code down here just so I can see this function. This is all kind of unrelated stuff at the moment. And so here we have, so just looking at this as well, none of this stuff we care about either. So all this stuff can pretty much go. I don't know what this nonsense is. I don't think I care about any of this stuff. Yeah, I don't care about any of this stuff. I'm going to get rid of the cluster table stuff as well. And what's the start point nonsense now? Okay. So again, just cleaning this stuff up. Here you can see us drawing our debug lines. We want to keep that in there because we're probably going to need those debug lines as we try to debug this, whatever the new code is we write. So we want that in there. This stuff here, we don't care about. This was the old way we were doing things, so that goes away as well. And so I think we want to start with all of that code out of the way. And probably, yeah, so probably that's really all we want. And so we look here and we say, all right, we've got the accumulation stuff going on, and that should, in theory, be not really doing anything anyway because accumulating is not going to be turned on at this particular moment as we're starting this. But we do want to maintain that. We probably want to get that working again eventually to check our results. And so we want the debug line output to be there. And so then here is the part that outputs sort of our test light at the moment. That's all good. And so now what we want to do is put in the part that actually works with the lighting probes. If we look at our game render commands, what we can see here is we've got a light probe count and a max light probe count and a light probe position, right? All this sort of stuff. And what this tells us is effectively what we... This is effectively an array that tells us what are all of the light probes that the game thinks are currently in like the active set, right? So this right here is our light probe position table. It's where the light probes are. This right here is our light probe irradiance table. It's what we thought the light probes were last frame. And again, all that is the incoming light at each of the 6 faces of the cube, right? So however many of these we actually used in this case, that they're coming through here, and those are the lighting values that we remember for them. Some of those lighting values will be full black. They will just be 0, 0, 0. Those will be light probes that have not actually received any illumination yet, either because they are new or because there's no light near them at the moment. Others of them will have a residual light value in it that is whatever their lighting value was last frame. And since we smooth our values over time, as I talked about yesterday, those values will sort of be used to heavily weight the results so that we only update the results by a little bit on each frame, right? So that's kind of where we're starting, and the light probe irradiance is a bit piggy right now because we're just using V3s for it. Eventually, I think we want to encode the lighting in there because we don't want to spend the extra bandwidth reading and writing that every frame. So I think we're going to want to sort of composite that down a little bit. But otherwise, I think this is basically where we're at, and we kind of, we'll have to see how it does. So if we now go and we take sort of a survey of this, the lighting solution itself kind of needs to work with these light probes. You can see here we've got the light probe count array here. And what I can do is I can just make sure that that's always the right size, and then we can work with these. The light probes themselves are positioned in a color. If we assume that we're just always going to be working with this, we maybe can just use these directly. I mean, it certainly seems plausible. So what we may be able to do is just say, look, we don't really care about this. It's not relevant. We don't need a separate version. We'll just work with the one that we've got here. And we don't really need to know anything about these light probes other than their irradiance and their position, for the most part, right? Now, there's one other piece of information we may need, because one of the things that we don't necessarily know is how many samples we added to each light probe on this time through. But one thing we could do, and maybe should do, is just assume that we, if we just assume that any light that's actually active on this frame gets a uniform set of samples, so one sample to each face of its cube. If we just assume that, then I think we don't need to track weights. So we either send out 6, 12, or 18 rays per probe, right? And we send one out of each of the faces of the cube. If we assume that we maintain that sampling pattern, then we wouldn't need to track a weighting value. We would know that every ray that comes in is always weighted the exact same way, right? In other words, the input values can be that can be adjusted ahead of time to account for what we're adding in, and then that would just be the end of it, right? I think that pretty much just works. And so basically you would sweep over the light probe irradiance table and you would knock it down by 0.95 first, and then you would just multiply your rays by 0.25 for 2 rays, or 0.125 for, 24 rays, or, however many it is. And you would just build the temporal smoothing directly into it. And so again, that just removes a step. That seems like a perfectly reasonable thing to guarantee, because I don't think 6 rays at a time is a totally reasonable stepping increment, I think. So we'll just say that that's true, right? And if we find that we really need things to be aligned to 4s, then we can just switch to octagonal sampling, which maybe is something we want to do anyway, because 8s are better than 6s, right? They line up better with machine words and ALU sizes. And so maybe we just start sampling the vertices of cubes in the future, right? And if we start sampling the vertices of cubes, then it's 8. Because, you think about it, there's no real reason you have to go out the center of a cube, right? I mean, is there? I don't know. Anyway, so that's all. That's all I'm saying. Not complicated. Just that's just saying what I'm saying. Nothing weird. All right. So if we assume that all that's true, and we have our light probe radiance sentence here, and we're doing whatever we're doing, and we come in here and we say we're not going to do weights, we're just going to make these things operate in place, then if I go to the lighting system, then what I would expect to see here is basically this accumulation value, right? The accumulation, the way we were doing the accumulation before, I think what we want to kind of say here is that the blending coefficients are just going to be specific to whether you've got permanent accumulation on or off. If you look at the accumulation C here, probably what we want to do is just think about the 2 values we're actually using and pass those down. So we probably want something like this. We want a preservation factor, right? So preservation C, irradiance preservation C. And then we want a new, or irradiance acquisition. Am I spelling that right? Yes. You can tell I don't work for Silicon Valley firm, otherwise I would know how to spell acquisition better than any other word. So irradiance preservation C and irradiance acquisition C, these are the 2 values that we're going to be using to blend the things together. And so we can set these to whatever we want, and you can see we were sort of already doing a little bit of that here. And so what we want to do is assume that our irradiance preservation value is going to be something like, let's say we want to blend it over 1/60th of a second. I'm sorry, let's say we want to blend it over 60 frames, so it's 1 second on a 60 FPS machine, right? If we want to do that kind of blend, then what we would say is, well, our acquisition amount is going to be 1/60th of a second, right? And our our preservation count is going to be the opposite of that, right? So what we would also know here is that, generally speaking, we could say that our preservation amount is just going to be the sort of complement of whatever the acquisition amount is. So we preserve whatever we don't acquire. And so that's just another way of saying, look, we've got some amount we're going to keep, some amount we're going to add in. We'll start and just make those 2 values. And I'll note them here. Waiting for new rays, waiting for old irradiance. Right? So then when we have our should accumulate here, I don't know that we really want should accumulate to even be there, because I think we're sort of having this either way. So I think if we have solution accumulating on, all we really need to do here is to set these values, right? So if we're trying to accumulate and our accumulation count is less than the amount that we wanted to do, right? Then what we do is we just set it. So our irradiance acquisition C is going to be 1 over whatever this total acquisition count is supposed to be. And then our irradiance preservation C, right, is just going to be 1. And so we keep whatever the old value is, and so it's not a moving average. We keep whatever the old amount that we put in there is, and we're just adding every time, right, to do a smooth accumulation. If, on the other hand, we're done, then we just say, oh, well, actually, our acquisition C, and in fact, I suppose this can stay. Our preservation C is always 1. Our irradiance acquisition is either, right, a amount to contribute, or if we're done accumulating, we just set it to 0. So this is if we want to take a long-term average over 5,000 frames to see what the result is, just to see whether the lighting converges to something stable, right? And so that's all we'd have to do there, because now we don't need this extra baggage. When we do compute light propagation, we can just say, look, the preservation will already have been factored in, so it's really just acquisition for you now, right? And off you go. Now, the problem that we will have here is that the way that we're doing our acquisition and our preservation, we probably want to factor this in the reverse order. So we may want to do this a little bit more squinky in the future. The reason I say that is because the simplest way to do this is now, once we have this information, what we would do is loop over all of the light probes and knock them down by the preservation coefficient, right? So what we'd want to do is say, all right, for each probe index here, as we loop over the light probe count that we have, so this is going to be in the commands here, but I'm going to actually just make that be a local variable. And I'm going to grab these other things out of here. So here we've got our light probe position and our light probe irradiance. So probe P. I'm going to do probe count. That's probe. Probe P and our light probe irradiance. And this will be our probe I or something, right? And so these will just pull these out into local variables so that they're easier to see in type. And I'll take the probe position here, and I'll take the light probe irradiance here. And so what I'd like to do is I'd like to go ahead and make this knock down the irradiance of each of the lights in question, right? So I'd like to say, probe I, light 0 times equals irradiance preservation C, and off we go. Right? So I just want to knock those down by whatever the preservation value is. And what I was trying to say before, when I say, and I'll put it to do here, so we probably don't actually want to do this here. It's going to be slower, I would imagine, to take the light probes and multiply them first by the preservation coefficient, then do the light transport, and then come back, loop over the light probes again to voxelize them. What we would rather do is multiply by the irradiance preservation coefficient when we actually do the voxelization, right? But the problem is we have the irradiance acquisition value baked in there. And so what we probably want to do is take the irradiance preservation coefficient, multiply in the inverse of that to the irradiance acquisition, so that we can just add into the unadulterated values first, and then do this to the accumulated values, right? Because remember, we should presumably be able to figure out how we would do that weighting. Now, maybe we can't, because things don't always distribute over sums the way we would like. In fact, I guess we could figure out whether we can right now. But there probably is some way to do it, is all I'm trying to say, without creating a separate buffer. Let's take a look. So let's assume that we want to accumulate these probe values. And so what we have here is we have a preservation value, right? And we want to add an accumulation value. And that's going to equal our new probe value, right? And so this is the equation that we're trying to create. And we know that we don't want to just add these two together. We want these contributions to be weighted in a particular way. And so our goal here is what we want is not this equation. We want the new probe value to be some kind of a weighting value. So effectively we want, and we know that it's balanced, I guess, right? We pretty much know that what we actually want is, t times p plus 1 minus t times a. We do want like a linear blend in here where we're saying we're going to keep, 0.95 of this thing, and so we want to add 0.5 of this other thing, right? Every step of the way. So we know that we want something like this, but the problem is rather than having each of these values, what we actually want to know is it possible to produce the value tp plus 1 minus t times a? Is it possible to produce this value, right, by instead computing a different form, an equation of a different form, which is just some other value, right? Like with, let's say we have a u and v values or something, right? Some other value u that we're going to multiply these things by, can we multiply at the end by u and instead compute p plus v times a, right? And so is it possible to get this result out of this equation when we can control u and v but not p and a, right? So we only get to set those two values. These are whatever they are, right? That's the question. And so, I guess I would say, looking at the way that this multiplies out, what you see is tp plus 1 minus t a equals up plus uva, right? That's the distribution there. And if we look at what these values end up being, it looks to me like we would need u to be equal to t, right? It would seem. And we would need u times v to be equal to 1 minus t, right? And so looking at that equation, I don't, my maths, as the British would say, is pretty weak. But looking at that equation, that suggests to me that if u, v is supposed to be equal to 1 minus t, and I know u has to equal t, then that means that t times v equals 1 minus t, right? And so solving for v, I would get 1 minus t over t, right? And so if I didn't screw that up, it means that we could set our values thus, so that we produce a u and v value that can be used in this way, right? Which allows us to multiply by one thing after the fact, while simultaneously just summing using this value, right? So I think, I would argue, not strenuously, because like I said, I'm not really a maths person. But I would argue that that's a reasonable approach because the math seems to back up that there's really no reason I would have to do it the other way. So I would think that if we started out with an irradiance acquisition and an irradiance preservation C here, that's the rates that we want to do it. If I wanted to call it something else, which is the irradiance blend factor, right? And this is effectively our T value. In here, we're basically saying this is how much preservation we want, in a sense, right? Would be what that is. So maybe I actually start with irradiance preservation C as the thing we want to do. And I'm going to set that to, 59/60ths, right? If that's the preservation factor, then what we would end up with is irradiance blend U and irradiance blend V. Looking at these equations here, the outermost preservation value is going to have to be equal to that, right? So this is straightly carried through. This one is 1 minus that value over the value, right? So here we have, and in fact, I guess I could write it this way. I'm going to actually call this the T irradiance preservation, right? Make sense? So that just is my way of avoiding this problem entirely. And so if we want to change how this is phrased here, all I have to do is say, okay, since we're going to multiply at the end by something, that something is just 1. I don't ever want you to change it. And the acquisition value that we actually were using before, that's the amount we multiply in, again, not going to be set that same way. So, when doing long-term accumulation for testing, we turn off the linear blend and instead just set the coefficients for long-term averaging. Right? So I think this very, very simple set of things allows us to do everything we want to do, and this part here now can just be ignored, right? Basically, we don't have to care. We can just, at the end when we want to go through and do something with our lights, which, we do want to do, here somewhere after we do our computations, once we want to actually voxelize these things or whatever we're going to do with them, we can do that blend value here. And that way, when we load them into the cache for voxelization or whatever we're going to do to actually output them to the graphics card, at the same time, we can do that blending. That way, we're not doing the blending as part of some, some separate pass that just wastes time pulling them into the cache and then out of the cache again or whatever else, right? Because we know we need those values to come into registers for other purposes in a minute, so we might as well just do the multiplication when they're already there and hot. So that, I think, is pretty straightforward. Now all we need to do is decide, okay, yeah, how are these things getting lined up and blended and voxelized once we have these light probes? And the answer to that question, I think, in this case is just, well, if we're looping over each light probe, it's pretty cheap for us to voxelize it, given the fact that we already, not cheap, but we already know how to do it because we wrote the voxelization code to do this like add probe to spatial index stuff, right? So you can kind of see here where we're, putting these probe pieces of probe information into the voxel. You can sort of see how we're doing that here. And again, that spatial index is something that I toyed with actually just sending down the spatial index. And the reason we didn't do that is because we were looking at how expensive it would be to blend these probes together. And it's pretty expensive per pixel to do that sort of stuff, I feel like. But it's always tempting to underestimate how fast GPUs are. They're kind of incredibly fast. And the fact that right now sampling from all of those voxels is apparently just a non-issue for the GPU, it's really bizarre like how fast it is. When you think about it and just looking at, the fact that it's sampling from 6 voxels and trilinearly interpolating all 6 voxels, like right now, right, is kind of ridiculous. So, when we think about that kind of going forwards, right, it's kind of interesting. What's going on there? Hold on a second. Oh, right. That's the edge of the lighting voxel right there. So at the edge of the lighting voxel, which you normally can't see if you don't go to the debug camera, it's a clamped edge. So it just continues to be lit for the rest of the place. Continues to be lit, man. Just like my Friday nights. So anyway, I think the idea here is just that we really don't know what we want to do here. It's an inexperience with just how fast GPUs can be in some of these circumstances. Because maybe we just want to keep what we were doing with our probe spatial indexing. I really just don't know. It's really hard to say. So I think I'm gonna say let's just use the spatial index that we have first. We're gonna use the spatial index to fill the voxel, and then when the time comes to start looking at the sampling again, we'll figure out whether really what we should be doing is just transmitting the index voxel down and letting the GPU deal with it, right? Because based on those sampling artifacts I was seeing, I'm thinking that we probably do want to do that because there's a lot of reasons why we would want to do that. We'll burn that bridge when we come to it. So if we now go to how this was working, you can see this add probe to spatial index stuff. What was that? Well, that was the thing we wrote where we have a light probe spatial index. In here, we can put in all of the light probes and where they actually are, right? And so if I was to call the already existing thing that does this, right, the add probe to spatial index, and I don't actually know if we ever called it. We don't, right? So if we want to do this, I want to do add probe to spatial index, right? If I want to do this, what I can do is here, where we loop over all of these. I want to add them to the spatial index here. Now, what you might be saying to me, you might be saying Casey, and you'd be using that because it's my first name, obviously. It'd be weird if you said, Brian or something, because that's not me. But if you were talking to me and used my first name and said, well, Casey, you just said we don't want to make a pre-pass over these things, which is not really what I said. Remember, I don't want to pull the irradiance into the cache. This is pulling the positions into the cache, which is a separate array. And it's a separate array for a reason. It's because that way it doesn't pull the irradiance into the cache if I don't actually want to look at the irradiance. So when we add these probes to spatial index, we're only pulling in just their location, because that's the only thing we actually need. So here what I can do is I can say add this probe to spatial index. The spatial index here is called the spatial index, I think. Just spatial probe index, sorry. So I want to do add probe to spatial index. I want to add it like that. You can see that we've got which index we're talking about. So it's this one. That's actually U16 here because we don't allow more than 65536 probes at the moment. We then have a probe min P and a probe max P. Like I said, we need to add that P in here. Something... Yeah, that looks fine. So what we want to do here is say, okay, we've got this probe. I feel like this probably should have passed the probe position in here. I don't feel like the probe min P, probe max P thing makes sense because in the event when you need to do a tiebreaker, you needed to load the P value in anyway. So I feel like this is kind of stupid and wrong. So I feel like what we actually want here is a probe P, like this value, right? These should have been derived at the head end. You know what I'm saying? So like I feel like these two values. So I think what we want is probe P minus radius and probe P plus radius. You know what I'm saying to you? Is what we actually want. And so I feel like this should be passed down like that. Because we're going to have to look this thing up to compute those values anyway. And then this thing just goes ahead and grabs it again for no reason, right? And so I think what we want to do is say this probe we should never actually have to query, right? So like this value here, right? You can see that this probe was only ever used to get that. And so I don't think we want that. We need to look up probes in this case to see which one is best. And if we really didn't want to bite that, which maybe sometimes we might find that that's too expensive in and of itself, actually. And so if it turns out that that's actually not going to work for us, then what we could do as well is just say, look, inside here we'll store one extra F32. So basically inside, you know, right, like you can imagine going into the spatial index, and instead of just a U16, there's also like a, right? And we would just look to see like, okay, in this cell, what was the most missing? I don't know which of those is worse. I suspect that doing it the way we're doing is probably okay at the moment, so we're going to leave it at that, but you get the idea. So now, if I look up one of these spatial probes, so I go ahead and grab group, oh, sorry, it's actually probe. Why did I call it probe B? Probe P. So if I say probe P of light probe index, that gives me, well, in fact, I guess I don't even need to do it there. Just do it right in line. Each probe's radius needs to fill the voxel to a certain extent, and it's hard to know how big we want that to necessarily be. But if we look at how we're, you know, talking about these values at the moment, if I look at add probe to spatial index, what you can see here is the get center of call actually produces a world space center. So, you know, if we look here, you can see us actually adding the cell dimension in. This is producing like the center of this voxel, right? Like where we actually think the voxel actually is, if that makes sense. And so when we actually do this add probe to spatial index, presumably the probe radius is actually in world space. And so we would just say, like, how big do we actually want it to be? And at the moment, we don't really know. We can tune this value. And it's just how much coverage. It's expensive because as the bigger we make it, the costlier it is to build the voxel in the first place, because each probe has to fill that many voxels. So it is an expensive operation to do, but the bigger it is, the better the lighting, in a sense, because it adds sort of a fill region around each of the light probes that will contain lighting even if there was no probe in that particular voxel square, right? So I don't know what that needs to be set to at the moment. I'm going to use a 1 meter probe radius in all directions at the moment. And so that's what we're actually going to look at there. But who knows, right? This is all kind of pretty seat of the pants, and we're going to have to sort of deal with all of the consequences as we go, right? All So moving forward, yeah, we're going to have to correct a bunch of stuff because we removed that light probe struct because we're just kind of working with them directly out of the gate here. I also think that maybe the spatial probe index thing doesn't... I feel like that could just be welded directly into the light solution. I don't know why we actually made it a separate thing. That was probably unnecessary, but, you know, we'll see. So when we do our add probe to spatial index, that should sort of put that into our voxel. Now, when we go later on, again, this now doesn't really have to be done in that way. And the reason it doesn't have to be done in that way is when we go to output our voxel now, if we want to, what we could do is say, well, why don't we just actually like get rid of all this nonsense completely, right? And there we go. And in here, let's just pull out the light probe that actually belongs in this thing, right? So what we could do is say, all right, we've got, you know, light probe irradiance values that we want to deal with here. We want to do the ear blend U thing, but then after that, what we want to do is just, you know, pack them up, right? So these values here would just be kind of copied verbatim. Directly into here, I think. Well, you know, I lied. That's not true. So we do have the problem of having to encode these things. So really, we are going to need a slightly different algorithm for that. So I guess what I will do here is I'll do this slightly differently. I'll say that in here, what we want to do is we want to do a light pack, right? Because that's what actually wants to happen here. Like so. Here's our irradiance packing that we want to do. And here's the values we actually want to keep. So So we need to generate an irradiance pack function, and that irradiance pack function needs to somehow figure out how it's going to represent light values in that way, right? And so what that will look like is something like this. We get in the light intensity value. This value is something between 0 and like the max light intensity, right? I mean, it could be anything really. So it's not 0 to 1. If it was, we'd just call this and be done, basically. So what we need to do is produce a value where we slide the magnitude into the alpha, and everything else is sort of... everything else is just treated as the color balance, right? The proportion of the colors. So if we want to do that, you know, the fastest thing probably to do in this particular circumstance, right, is to just say, well, you know, we could even Euclidean norm these things. Like we could do just a squared, you know, without square rooting. We could just do a squared version and then square root. We could use a 1 norm for them. We could just use the maximum value. I guess I would probably go with maximum value. Just offhand. So I think what I would probably do is say, you know, whatever the max value is. So I want the element maximum, which I don't think we actually have. So anyway, I want the maximum value here, so I'm going to assume it's x. And then I'm going to say, look, if the maximum value is less than light y, we take it. Actually, I guess I could write it this way. I mean, that's actually what we want, right? And so I think I don't have a triplicate version of that, so I'll just, sort of do the currying version. So producing the max value there, if the maximum value, the result here will be 0. If the maximum value is greater than 0, then we can actually do the pack. Otherwise, we can't. And it's just going to remain 0. So if it has no intensity, it has no intensity. So we look through here and we say, all right, if there is a max intensity, then we can do the pack. The pack is going to be whatever the incoming value was, x, y, z. These are the color balance values, and then that maximum value would be going in here. We need to balance these out, right? So we need to encode these in a way that actually works with the encoding, which is supposed to put the magnitude in here. So what that means is the maximum value has to come out. We kind of need the inv max v, right? So the inv max v is going to be 1 over the maximum value. We need these guys to sort of represent that inv max v, right? And furthermore, we also sort of need this max v value now to be encoded between two ferns, right? As it were. We need that max v value to be relative to max light intensity. So this value here, we need that to sort of be, we need this to be bounded in that space, because it's going to be reinterpreted in that space. So the max value that comes out can't be, can't be higher than this. And the number from 0 to 1 that we encode is going to be reinterpreted as part of this. So we need the max value to basically be like divided by the max intensity, and we need it to be clamped, right? So we kind of need in here, this, alpha value. So we need this alpha value here. We need this thing to be reinterpreted in terms of what percentage of the max light intensity it is. And then we also need that value to be clamped because it can't go out of the range of an 8-bit value, right? Again, a lot of dancing around here that we have to do, but that's just, the nature of trying to pack HDR values. And we can do a much better job of this in SIMD, certainly. So when it comes time to optimize this stuff, assuming this shows up on the profile, this part is slow, right? Off we would go. So anyway, let's go ahead and yeah. All right. So I think what we want to do here is not sure which order I want to take these things in. So I think let me just finish what I was doing here before we go any further, though. So we have a probe index here we need to use to look up which light source we're actually talking about. And what I may do is actually grab that out first, right? And so here we have each of the light values in question. And I think now that's basically what I need, right? So I need to look up the probe index, which we haven't actually pulled out of the voxel, but we will. We need to irradiance pack each of these values. And before we do, we want to like multiply them by the blend coefficient so they reduce down, right? Then we're just going to stuff them, as you can see, right into here. And so I think that's pretty much all there is to that. Getting the light probe value out, since we have, you know, the X, Y, and Z here, if we look up that spatial index, let me just see where we're at here. So get corner light index, I'm not really sure. We have to go check to see. I don't even understand what get corner light index is supposed to do here. Like, I'm not sure why that's called get corner light index. I think that was probably because we were thinking about this in terms of like yeah, I mean, it looks sort of like what we were doing there is saying. So let me take a look here. So when we do add probe to spatial index, I'm not sure why we're calling it get corner light. I don't quite understand. Because if you look at what's actually happening, it's just figuring out what the closest one is to the cell center. So it's not the corner light index, it's the center light index, right? And so then when you say like, when you say get probe lighting for, and you know, here you say cell P, you know, this is all totally fine. The problem is that when you looked it up in the first place and you wanted to know, right, like, so get probe lighting for example, right? When you map this into the grid, you didn't actually want it to give you the grid cell you were in. You wanted it to give you which probe was the one that is less than your spatial partition position in each direction. Which cube's center is the next one down, right? So I do feel like we have sort of a fundamental stupidity happening here. This probably has to get fixed. And so I will fix it, but it looks like we've written this a little bit bogusly, which is probably because we just kind of wrote it to get one in there and we didn't think it through as good as we probably should have, right? So, you know, I'm not going to harsh on us too much, but it's not great. So in here, what we really, you know, we're really not calling, this is not really corner light. I think that's just dumb that that's what that is. But so we're going to say get corner light index. This is going to be U16. That's like, you know, probe index pointer here. We're going to get that. Actually, I guess I could just do this. And so we pass here the solution probe spatial index, or whatever it was called. And then we need the actual cell coordinates, and those coordinates we know are bounded, right? So we know that we're not going to get anything out of bounds here because we're only iterating over voxels that actually exist. So in this case, right, we go through and we are sending out basically the values based on what we find in the voxel at any particular location, and that's based on the whatever it is the voxelization of the probes to begin with tells us is there. That's what we send out for our actual irradiance, right? And so I think that's sufficient. The only thing now is we wouldn't actually get any light even if all of that worked correctly, because none of these probes has any irradiance in them. And so one thing we would need to do at some point is actually assign some irradiance to these probes. And again, that's actually something we can sort of crib now from this previous voxel stuffing. What we can do is we could do the same thing with our light probes. So here where we actually kick the probes down, we can put in some debug code here that actually stuffs the irradiance of those light probes sort of based on the same stuff, right, if we want to. So we can just kind of say, like, hey, this light P, right, like maybe we go grab that. And so we have this debug light P here. We're going to grab that out. And when we come through here, we can say, well, let's find out wherever this light probe actually is, which is, something like this. And so if we actually know where this is, then we can use the exact same like debug light situation here. We can compute this same light situation and sort of use that to stuff the values of our light probe instead, right? So if I was to take like this, let's say, and stuff that in here, then this becomes debug code we can use to stuff the light probe irradiance values as well. Looking at them here, we could say, well, the light probe irradiance value in this case is going to be, wherever the light position was, which is this, minus whatever our world space position is, which is that. The distance is still the same. The n value is still also the same, right? I don't know why that is written twice, but that, yeah, I guess that was just bad code from before. So we take the, this is the direction to the light source. We normalize it, because we're going to use it in a second. We do the light coloration here. We do need that light RC value, but we can, again, move those things up here. So like these two values we can share between the two sets of debug code, just like we share the light value, right? And so we can compute all of the lighting information this way, and then all we have to do is when we come down here, we can just stuff whatever these values are here, right, into our actual irradiance table. So for the light irradiance here, we would just say light probe irradiance. That's our irradiance table. And each of these just tells us how much light there should be. So in this case, we have each direction. We've got, the west, east, south, north, down, and up. And now we just need some idea of like what the light color actually is, which should be fine. Because, oops. And that's something we can also set up here. So that gives us a way of stuffing our light irradiance values at the outset, and we can stuff the light probe irradiance values. We can stuff the light probe irradiance values first, then we voxelize them later, and now we can see whether that pipeline is working properly. Because if it is working properly, we should get some sort of a lighting, sort of a crappy spherical lighting thing like we had before, just stuffed in there, right? And so this way we can sort of debug that process as well. Now, building the spatial index for these things, I believe, like, I don't know when we actually, if we ever tried this or not. I don't think we did. And so if you look at, like, the spatial index stuff, one of the things about it is I don't think anyone ever initializes it, right? So we kind of have to actually set this stuff now, right? If we want to use this thing, we're going to have to actually set it to something. So when we come through here, we're going to have to set each of these values, and the light index as well has to kind of be allocated or, you know, pointed to something or something, right? So when we do init lighting, that has to happen. And, you know, looking through here, it obviously doesn't. So, you know, one thing we have to do here is say, all right, the light index here, that has to be pushed on there, and we need, you know, to know what the voxel size is actually going to be, and I believe that's something that's just hard coded at the moment to what its maximum actually is. So you look up here and you can see what it is. So we need the cubed version of that, right? So the light lookup voxel dim, that's going to have to happen 3 times, or 3. You know, it's cubed. That's how much we need for our storage there. And then when we come through to the end lighting computation, we need this stuff to be set up, right? Like someone has to set it up, that voxelization. And the first thing we would need to do is actually clear it as well. So we would need to do a 0 array. And we would need to clear out the size we expect to use. And then we would also need to set all of those other values that we care about. So all of this stuff here, we would need to update. Now the total cell count, I don't know who's actually using that, but I'm assuming that we could set that as well. So no one's using it at the moment, but we could. It probably is handy anyway. So the total cell count here is always just this. And so we kind of know that you know, is something we can lean on there. So when we want to clear this array, we can just say like, hey, it's this many, right? But we also then, every frame, we could, you know, we don't know if someone has adjusted this stuff. So we also need to set all of the values that have to do with the voxelization. We need those values to be set in here, right? So all of this stuff has to get set before we can use the voxel effectively, because otherwise it won't line up with what we're doing anyway. And so we need, like we had down here, where we've got sort of this information that's coming through in setup. You know, that stuff kind of has to be captured as well. Let me just grab this stuff here. In fact, this stuff should be kind of put up to the top. And then down here, I just want to grab this real quick. So the in voxel dim and the voxel min corner, right? Those come through the setup. So the voxel min corner, oops, comes in here. And then, you know, we need to know the cell dim and the inverse cell dim for our purposes. And at the moment, right, those are not things that we actually know. Oh, I guess they are. No, they're not. No, they're not. It's the dim power 2 that comes in here, right? So we don't actually know that. So what we actually want to do here is start to talk about, like, you know, we want to be able to compute these values efficiently, is the thing. And what you can see from some of these is it's kind of hard to do that in some, based on what we actually know in some of these cases, because we're providing only the minimal amount of information, and it's also kind of scattered around a little bit. And so we end up in a situation where, like, we're probably not doing this as efficiently as we could be either way, but we'll, you know, get there as we go. So if we take a look at what we know the inverse voxel dimension is, well, the inverse voxel dimension, the inverse voxel dimension here, yeah, that, in fact, that doesn't even matter. I don't even know why we're looking at this value. This is not relevant to us. Put that back down here because we don't actually want that. There we go. So the inv total dim is really the thing that tells us the piece of information we wanted, but it doesn't really tell it to us in the way we want. So if we take a look at how big a cell is, well, right, we know what the dimension is, and we know what the inverse of the total dimension is. So the inverse, like, of a cell, for example, and the inverse of the total dimension are related to each other by the dimension. Unfortunately for dim pow 2 is something we don't actually know because we only have the vox dim coming in, and in order to figure out what power of 2 it is, we would have to bit scan it, which seems bad. Which makes me think we maybe want to specify the voxel size as a power of 2 because it is something that you do want to know. And we know that we can never really use a non-power of 2. You know, in terms of the way the graphics card is going to work, we're always going to want to send down anything that's voxel. We're going to want that to be a power of 2 for sure, right? And also for facility of working with it on the CPU, we probably also want each dimension to be a power of 2. They don't necessarily have to all be the same, but they do all want to be a power of 2 probably. And so it's probably the case that we, you know, looking at how this this is shaking out, I think that also is something we probably would want to fix, right? But again, moving forward with what we have as we have it, and maybe I'll ping pong back to the old way of doing the test and replay around with how we're specifying some of these things. But for the moment, just to, you know, play with it here, I'm going to actually just derive these values directly instead. And so what I'm going to do here is when we did enable lighting and we have light bounds, right? You can see in here when we record those light bounds, right, into the render group, I'm assuming... Don't we have, because in here, I thought we had to set, I thought we had to set the inv cell dim. Am I wrong about that? So, sorry, that's not the one I'm thinking of. What I actually mean is the voxel inv total dim. Somebody has to set that, right? I mean, it's getting set in the actual thing. Set light bounds. That's what it is. So inside set light bounds here, right, when you send these two things down, I'm not really convinced that, right, like this seems to be sort of a little bit of the issue. So when we have that set light bounds call, I think that's kind of the part that's a little bit sticky here. And so if you take a look at when this is getting pushed on at the beginning, I feel like that's sort of more the thing that we wanted to look at in the world mode where it actually occurs. So if I look at set light bounds, if you look at where that's actually happening, you can see that like begin lighting computation is the thing that happens right before it. And so what I might say is, like, maybe that is actually the way this should work, is instead of, you know, this is maybe the wrong way to look at it. Maybe what we actually want is this call here should actually be occurring in here. So like, you know, the lighting is enabled or whatever. And we are then going to set the light bounds, or, you know, we could do them in the opposite order or whatever has to happen, right? Who knows? But that way, inside begin lighting computation, we can store more information about what the heck we're trying to do here. So when we pass this in, you know, we just pass light bounds directly, and this thing can store all of the stuff that it wants to know about the light bounds without having to like sit around trying to reverse engineer what the heck it was from inverted versions of itself and everything else, right? So if we were to switch to doing it that way, then this is kind of nice, because then inside begin lighting computation, what we can actually do is set up all of this stuff in there, right? So this can just happen in here. We know what the min corner is because it's just the light bounds min, right? We know what the cell dim is because it's this dimension here. Divided by the number of cells in each direction, right? So the cell dimension is just the light dim. You know, it's a Hadamard quotient, right? But we'll deal with that in a second. And the NV cell dim is just 1.0 divided by, I don't know why I got rid of that. It's just 1.0 divided by the cell dim. Right? And so really that gives us a nice way of pushing all of that information down cleanly, because now we're just sending down one bounding value at the start, and then all of these sort of like values that we're going to need that are dependent on that value just all get computed in one place. The problem that we have is this dim pow 2 bit, because at the moment we do know how big the voxel actually is, we just don't know what its actual power of 2 is, and that makes it a little bit harder, right? So when we want to actually compute the cell dim, that's not so bad, because there we just need the arbitrary like count, and that we do have, right? So we can do a Hadamard quotient here. Do we have a Hadamard quotient? We don't. All right, so I guess we'll have to do a Hadamard product. I'm not going to go write a Hadamard quotient just for this. Of the light dim and the inv cell count. Right? And so we know some of these things, right? Like this right here is the inverse cell count. I mean, that's what that is. So we know we can actually create these things as necessary. The vox dim here is specified as a part of the command structure always. So we know what that is going to be, and this is the inverse vox dim. So I'm going to call this vox count here, or cell count, and inverse cell count, right? So then when we come through here, we can say, all right, we know that the cell dimension is going to be the Hadamard product of whatever the total lighting bound dim is, right? And the inverse cell count, because that will divide it out. We then know that the inverse cell dimensions is, well, it's the opposite of this, right? So it's 1 over that value. And so the only thing we're left with is this value here, which we don't know. And this wants to be, you know, set. We kind of know vaguely what it is, right? We know that it's the cell count. And we could sort of just do it this way, where we say, look, at the moment we kind of know what it is. It's just going to be whatever that cell count is, the power of 2, right? And I don't know if we actually have any functions that do that scan. Yeah. So we do kind of know, like, we can find these out, right? It's pretty easy for us to see what they are. So if we assumed it was a power of 2 first, then it's actually not very hard for us to find out what that power of 2 is. Yeah. So, I mean, I guess we could just stuff that. The other thing we could do here is just change the way we're defining this, right? So inside the renderer, if we look up here and we say I think this is just a saner way to do it. So this way we would say, look, you know, it's going to be specified as a power of 2 as well, and so here you can just kind of get that information out. And maybe we hard code those a little bit more, or maybe we make them looser, I don't know. But, you know, at the moment we'll do that, and then we'll maybe pass that down as something here that we needed. This code desperately needs to be cleaned up. I don't want to start cleaning it up till we actually know that we've got it the way we want it, because otherwise I'm just like burning time. So in here, now we can get all of the information we need for our voxel, and it can at least be set up properly. It can be cleared. And then in here, we can voxelize into it, which we want, and off we go. Now, it kind of doesn't make much sense to do this clear, to be completely honest. So I think what we'd probably rather do is when we come up here and we do the initial allocation, right? We know that it will be cleared then. So I think what I'd rather do is when we process it here, I think this is probably the time to clear it. So what I think we should do is say, let's grab the probe pointer. Like so. And this can be made much faster, because right now we're doing a blind lookup here, whereas what we could be doing is just stepping linearly through the voxel, so I could just increment this pointer every time and be done, you know what I mean? And in fact, you know, that might be the smarter way to do it just to start with. So what we could do instead is just say, yeah, forget about it. Let's just assume that what we actually wanted to do was take like a pointer here and say, let's start at the initial indexing of this thing. So we've got the solution light probe index dot light index, and we're just going to step it. So each time we know that the probe index is just the probe index pointer dereferenced, right? So we don't really have to do any work to get that. We don't have to call get corner light index. We don't even have to build the cell cord. All we're going to do is just look it up. And then when we're done with it, right? So now that we know what the probe index actually is, we can just go ahead and clear it as well, right? So that way we are reading and clearing it at the same time. We don't need a separate loop at the head end to like deal with that, right? So we read and clear and pack all in kind of one go, and I think that's probably better than the alternative, because we're not doing separate passes for no reason. All right. So now we more or less know when we do light probe calls, we kind of need to change these to be just passing the information we actually have rather than these false sort of probe pieces of information, which are gone now. So if we look at how we wrote this code, let's sort of take it step by step and sort of replace it. So in here, where we look, we can see all of the sort of the red nastiness here. What we need to do here is get the light probe position separately. So we kind of have a light probe P, right? That's going to be coming this way. Actually, and you know, these are probably things that we can just have pointers. I want to say these can just be off of the solution as well. So I think we probably want to do it roughly like that. And then, you know, we know that the origin is just going to be looked up like this, right? And then at some point, we're going to need... okay, so here's like the sampling and whatever, and at some point we're going to need, although I'm still not actually seeing it, at some point we're going to need the actual compositing values. You can see that happening here. But we really don't need a position anymore after that. So this can just be a light probe irradiance value that comes back from this call, right? And then I think we're pretty much done. Yeah. So I think we can just modify that code to be pretty straightforward. When we call this, we're really just asking for the irradiance. And so I think that solves that problem. The solution itself needs to have the pointers to the actual arrays we care about here. So we're going to need, like, you know, the light probe P here. And we're going to need the irradiance as well. And this is just to avoid having to pass them down. They are in the render group, so they're easy to come by. But we just don't want to have to pass those around because we know that everybody who's operating the lighting solution is going to have them, right? Yeah. Get lighting from probe. Again, that is, I think, just this. And now we actually have to change those things to work with those. So when we do, this is actually probe irradiance, right? In both cases, and light in this case just needs to be replaced there instead of color. And I guess I don't really know, like, in terms of the way that these are working, does anyone ever care about the position? And the answer seems to be no. So I think that pretty much all of these want to work on, like, almost everybody wants to work on just the probe irradiance, but for this one right here, which needs the actual position. Right, this one is the only one that actually needs that position. Now, I don't think it makes any sense to actually call getProbe here, but I mean, maybe we will. It seems like kind of stupid, but you know, whatever. So when we're actually calling that getProbe call here, what we really want to know is just what the existing probe P is, right? So we really just want that is all that we actually need. And so here what we want to know is just, well, we've got the existing index. All we really want to know is, like, all right. Oops. You know, what's its position? And that's just, you know, a pretty trivial thing to implement. So I think everybody else just wants the irradiance value. So I think everybody else can just work, right, by just replacing it with this for now. And again, this code probably needs to be, like, improved quite a bit. It's not great at the moment, and so we'll, you know, but that's the nature of code. It goes through some bad states before it gets to a good state, and that's just how you have to program if you want to program well. If you try to make sure that you start off with a good state, you will just always have either no code or bad code. All right, so I think we're mostly good. This is this, and this is that. What else we got here in the error list? Same thing, I think. Yeah. And get light from probe. This is, again, just all right, this is just the change of name there, but I think otherwise we're good. What else you got? And so this needs a variable type, obviously. I guess that needs to be casted to an F32 because it's expressed as a double at the moment. The light probe index total cell count here. Spatial probe index. Ugh. All right, sorry. Yeah, that's just a lot of bookkeeping. Looks fine. All right. So the total cell count here, this push array needs which arena, which is easy enough. The light bounds, when we call set light bounds, this is just called group, not render group. Here we don't have the commands readily available, so we really need that. And then this vox dim here is supposed to be cell count. I changed the name of that and didn't update it, right? Is there something, what is it complaining about here? Oh, yes, this is backwards. And so now I think we've got those sorted out. What else you got for me in end lighting computation? We've got issues here. It doesn't like that colon. Can't blame it. I'm not sure why there is a colon there. The light probe count here, we don't set a lot of these values, so we're going to have to go make sure these are set too. We're just going to have to go through this and clean it up a little bit. And clamp 01 of the light RC times the light dist. What is it complaining about? Oh, there's a previous value of it. Sorry. I'm going to call that light color at the moment. Oops. Just so we can make that work. And then I don't know if we defined a V4 that's a V3 version. We did, so that should work as well. So actually, yeah, these, this I was a little premature on. Remember, this actually stores full values. These don't have to be packed or split in any way. They're not HDR values. They can just be arbitrary floats. So it's actually just the light color times the brightness in that direction, and we're done. Let's see what else we got here. That's spatial probe index. We don't need any of this stuff turned on. And then I think we're compiling. Yep. And so the only other thing I want to do here before we end for the day is we didn't initialize these values, so they're not going to work, right? And so what we want to do when we first begin the lighting computation, or really we can do this at any time, but so maybe we do it here because we could do all of them here. What we want to do is make sure we set all this crap, right? So all of this stuff here that we're just kind of duplicating because we want it to be centrally indexable by anyone who just gets a pointer to the lighting, like because we have multiple threads who then come and have to look at this stuff. What we want to do here is say, all right, like let's actually set all these values. So the light probe count needs to be equal to the actual number of light probes that got recorded, right? And the light probe P needs to be set as well, and the light probe irradiance needs to be set as well. Get those wired up. And then I think, we're fine. And so this is going to be, super buggy and crashy and weird because we just kind of wired everything up. So I probably won't debug it today. I think what I'd like to do is, next weekend we'll start playing around with it. Try to smush that code down into something more reasonable. Well, actually, I take that back. I might debug just this because this is probably pretty easy for me to debug. But smack the code down a little bit, kind of smooth it out a little bit, and then start to actually work on getting the light transport up and running. Because this is all this is going to do now is just actually have the light probes flow through properly, but that's all it will do, right? So I just want to take a quick look at that while I'm still thinking about it. Add probe to spatial index is here, and you can see it looping over the indices in question. The map into grid, the one thing I have a question is this actually clamped? Yeah, so this is not clamped, so, you know, that's why we're getting that error. This is just kind of stupid, right? You want these things to be clamped so that they... Yeah, I mean, this is just kind of dumb. So what you want to do here for map into grid, and you know, if we look... Let me just take a look at who's calling that at the moment. Yeah. So what you probably want here is map into grid is something that probably wants to be more of a like rejection based thing probably, but for the moment I guess I won't do that, and we'll kind of think about it a little bit differently. But what we'll say is, you know, when we do map into grid, I will then take the resulting UVW indices that come in here, which is probably not the best name for those. We'll take those indices and we'll floor them out, right? So we'll say like, or we'll clamp them, right? Do we have a clamp for integers? So like this, right? So each of these values, what we'll do is we'll clamp them. And we'll say that we want them to clamp out between the dim values here, right? So when we have the spatial index dim power 2 nonsense here, right? We're just going to say, look, you can't go outside those bounds. Now, the clamp itself doesn't really do quite exactly what we want, because you can see we'll allow the max value to exist. And we actually want the max value to be out of bounds, because there is no cell there. That's like the outer bound of it, right? So we're actually clamping to 1 minus that value, and that's what we actually want to return. Okay, so yeah, like I said, I wasn't going to really debug it, but I'm probably going to debug a couple things because that's obviously stupid, right? So we're going to fix that. And we might fix a couple if there's any other obviously stupid things going on. But we'll leave the actual making of the code nice till next weekend. What is this complaining about? Oh, whoops. UVW is not what I wanted there. I was trying to clamp the cell coordinates, not the location. What's interesting about the UVW is, I mean, in some sense, I feel like this probably wants to actually be allowed to be completely bogus. Like, in other words, it probably wants to be computed afterward, but I don't know. Like, maybe you want it to always be 0 to 1 anyway. That's really hard to say. So I'm not sure what that should be. If you place it up here, yeah, there's just, you know, I don't know. So I feel like maybe we want it to always be more bounded. I'm going to put to do on it. So yeah, you know, what do we want to do there? I'm not sure. We could also clamp that value, and then it would always be correct. I don't know what we want to do with that, but, you know, we'll see. Okay. So actually not as bad as I was expecting. It's actually doing something at the moment. But yeah, obviously totally wrong. But I'm going to leave it there because we'll go ahead and actually try to work these out more directly in next weekend when we'll actually start to work on the light transport part. We'll get the light probe stuff cleaner, and then we will try to figure out how we want to start doing the light transport stuff. We've got it sketched in there, like it's actually got some code in there that sort of does it, but that's going to have to start improving. All right, let's go to quick Q&A. Room. Why does the Handmade Hero channel not have the game development and programming tags? So it sometimes does and sometimes doesn't, is the answer, Roman. Basically, the way Twitch chose to implement their system, because, they are web programmers, I guess, is that rather than allowing you to set what your tags are going to be in some kind of a groups, and then when you start streaming you say which one it is, which is exactly what you would normally do, they just clear your tags every time. Every time you broadcast, they clear your tags. So the reason that we are not labeled as game development programming is because I got tired of every time before I stream having to pick all of our tags again, right? So I just got sick of it. It was too rage-inducing because every stream it's the exact same tags. We always do the same thing. We do game development and programming every stream, every time. And I don't really want to have to go set up our tags every time. For debug text, no, we haven't put in a separate pipe for non-lit rendering yet. Do you have any examples of good written software open source that you would recommend someone to study or that you yourself have studied in the past? I couldn't say for sure. So I don't know. I don't spend a lot of time reading source code. I read mostly technical papers, and I just take people's word for it when I read, like, here's how it worked, right? I don't usually go read their code. But, I guess what I would say is I would be shocked if, say, the Doom and Quake source code wasn't really good source code. Like, I would be shocked if it turned out that the Doom source code or the Quake source code wasn't really good. I bet it is. I just don't think you can make Doom and Quake in that era without the code being good. I just don't think it happens, right? So I would say probably that's where I would look first. I didn't read them myself, but I would be pretty surprised to find that wasn't good source code. Where's the puss? She is outside the room that I'm streaming from. That is why the puss is like, I usually close the door if the puss is already out there, because that way there's not as much noise coming from outside. But you know, I don't think this color scheme has a name. I made up this color scheme. This is a new one. Um, so I made it up and balanced it out. I think I've done a future revision of the color scheme as well that's a little bit different. That's on my new editor. But it's pretty similar. Alt overflow. How can we improve the web? Just burn it down, man. Like get rid of all of it. Um, Start over and make things be peer-to-peer again. Like just, you know, if Microsoft had actually known how to make an operating system that could talk to other that where two computers could talk to each other, we wouldn't need any of this garbage anyway. So, you know, as far as I'm concerned, we're living in 1970 right now, and everyone has a terminal connected to a mainframe, and it sucks because it always sucks. It's never going to be good, ever. In the history of mankind, 3,000 years from now, it will still suck to connect to a mainframe. For all the reasons that it sucks. Latency that is insurmountable, you cannot, it's insurmountable. You can't, there's nothing you can do about it, right? It's the speed of light. Until someone breaks the speed of light, you're screwed, right? The latency is bad. The politics of it are bad. It centralizes the control of things into a handful of people. The ownership is bad. It prevents you from being able to actually like have your own computing environment and control how it works. We're in 1970 again. Somebody needs to be Microsoft. Someone needs to be the Microsoft of 1980, right? And you need to do that. And you need to be that in 2020. And just get rid of it. Get rid of it. Does anyone connect to a VAX anymore? No. And that's what we need. We need someone in 20 years to look back and go, oh, that's weird. Like, you mean to tell me everyone, there were these giant rooms filled with computers and everyone like called over what's essentially like a phone line to them or something? That's absurd, right? We'd be able to say the same thing about cloud computers. Like, there's a giant data center with lots of computers in it. You didn't just have it at your house? Like, what? And like, you mean to tell me that you used the like internet backbone instead of talking between you and the person you're trying to talk to? You like talk to some giant corporation first who like read all your messages? What? And you'd be like, you need that to sound as stupid today as putting an acoustic coupler modem on your VT100 and calling a VAX sounds to us today. But that's what you did in 1970. 1975. Someone had mentioned during the stream perhaps you needed 1.0 minus urblend U, but I had 1 minus urblend U. Why would that matter? Not sure why that would ever matter in that circumstance, so maybe you guys are saying something I'm not understanding, but like, you're talking about this line of code, right? Is that what we're talking about? Or is this something else? Is DirectX dependent on the C runtime? Can be used without it? So I'm not really a DirectX expert because I don't spend a lot of time programming it. But my assumption is that the reason that there's some confusion about this is because people don't differentiate between DirectX, the hardware API, and DirectX, the library. So if you're talking about DirectX, the like library with all of the like tools and crap in it, and like the matrix routines or stuff. I mean, I remember there being like a bunch of stuff in DirectX. That is almost certainly dependent on the C runtime and probably can't be used without it, right? But DirectX, the hardware API, if you just want to like get proc address, or you know, get pointers to the COM objects that implement DirectX or something, that should just work, right? You shouldn't need anything. You don't even need an import library for that. All you need to know is the layout of the virtual table. So you need the H files. And you could even cut and paste, though, the definitions. And you need to actually query where those vtables are, which I think you could probably just do with get proc address, I think. Now, you need to hard code the GUIDs in your app as well. I mean, but that's what happens anyway. Like, that's in the H file, it's going to hard code the GUIDs that you query for. But again, not something I really do, but you should be able to do that stuff. So you shouldn't need to link with the real DirectX library that might pull in the C runtime library and all that garbage. Okay, I gotta answer some questions about these lines because I'm not sure why this is causing so much confusion. So let me just walk through it. So T irradiance preservation is a number that is between 0 and 1. And you can see that here, right? So urblend U is by default, it's between 0 and 1. It's going to be, well, I mean, here is the actual value. I don't want to try and do that in my head, but, you know, it's this. And so if you think about what 1 minus urblend U is going to compute, it's just going to compute like 0.02, right? It's not quite that because you have this 3 repeating, but you know, it's within the ballpark. That's what 1 minus urblend U is going to do. Now, in terms of what happens with this expression, this is a floating point value. And this is an integer. So it's going to convert this integer to a floating point value. Now, it is true that you do need to watch out for that sometimes if this is a variable or something. But in fact, if it was a variable, I would have gotten a warning. So if, for example, I had done something that it couldn't see. So like, for example, let's suppose that I took solution debug line count, which is an integer, and I put it here. It would have issued a warning, I believe. And the warning is just that it can't necessarily do that conversion, I think. All right, that's a little bit weird. So I'll be honest, I'm not sure why it didn't issue a warning. I would have wanted it to, but it didn't. Did we turn it off? We may have turned it off. Let's find out. I really should rem these in here so we know which ones they are, just for quick reference, but let's take a look. Nameless struct union. Unreferenced formal parameter. Local variable. Removed function. Conditional expression constant. So I guess I'm not sure why it's not warning us about conversion there, because it should be. It can't represent an arbitrary U32. And I'm not sure why, unless I'm missing one of the warning disables. I'm not sure why it isn't warning, because my recollection is normally it does. And I don't really need it to, because most of the time I'm okay with that. but my assumption there would be that it's not really a problem per se. So let me just check. And the other thing I'm thinking is I wonder if is it because so is it because it's never used? It may just never actually be producing this value, is the other thing I was thinking. So I also kind of wonder if, like, we need to use it. Yeah, I got nothing. I don't know why it doesn't issue a value, an error there, because I would have assumed that we would get an error on that. And I don't know why we're not. Normally, if you do an int to float conversion implicitly, it will give you some warning. At least that was my recollection. So, I mean, I'm assuming, unless I'm just going crazy here, at the very least, like, that ain't gonna work, right? You would think it would tell us, hey, I'm worried about this, right? Yeah, float to U32x. And that's when it knows it can do properly, right? It's looking at the value 1.0 and it knows it can do it, so that's a little bit odd. Looking at floats in here, debug light p maybe. So if I said debug light p x equals, some value here, then I'm assuming that it wouldn't issue a value if it wouldn't issue an error if it knows it can place the value in there safely. Now, I don't think it would be able to put all values in there safely, because I don't think, for example, if I was to do S32 maximum, it shouldn't be able to represent that, and I would hope that it would give me an error. Maybe I'm wrong. Yeah, that's really strange, because I'm pretty sure that there would be no way for it to actually do this operation, right? This operation doesn't work. And I would have expected us to have turned it off in here, and that's why it's not happening, but that doesn't seem to be the case. Is there some other -WD that we're doing that I missed? Yeah, I mean, I don't know. That's really strange to me, I guess is all I would say. Because, like, for example, if we look at what actually happens here, I mean, let's just do it, right? So let me go ahead and set this to -OD, right? And let's go ahead and run the code to that point, and I'll just kind of show you what I'm trying to say here. So if we were to set a breakpoint where we were going to run that particular piece of code, where we do this assignment here, right? So if we look at what we expect to find here, I guess I should probably also put S32 maximum, because I suppose I can't probably look at that in the debugger, yeah. So if I was to also have a value here, and now I can just do it directly, so we'll do it this way. Test val equals let's say U32 max, right? And test float equals test val. I can also do it the final way and say, round trip equals U32 test float, right? So if we watch what happens here, and we just look at the process of shuffling these things around, hey, look, I finally got the warning. So now I got the warning. That was the warning I was talking about. So let me see how smart it is. Yeah, so I'm just really confused. I don't quite get I don't quite get it. How it's all right. So just to be clear, this is what I would expect. If it sees a value, if the compiler sees a value it knows it can convert to a float exactly, I would expect it to just accept that value. And that's what I assume it's doing here. If you use a value that it doesn't know, which in this case, right, it maybe does or doesn't. It depends on how much analysis it's going to do. Is it going to look and see that test val is set to 5 or not? And the answer appears to be not, right? Because it looks and it thinks it can't do this, even though this was possible, right? So I'm just assuming that's an analysis problem. So it's going like, oh, I can convert a constant to an F32, and I know it's fine. But I can't just convert some random U32 to it, and I didn't go to look to see that that would actually work. So you know what I'm saying? So this is what I would have expected, but what I don't understand is why I can't do that same thing here. So integral conversion aside, it looks like this is not an error or something. Yeah. So somehow when it does the integral promotion, right, it doesn't think that either of these two is a problem. Like, no matter what it decided to do here, if it decided to convert them both to integers or it decided to convert them both to floats, there's a problem, right? In either case, it should have been giving me the same warning it was giving me here, because all I did was the exact same operation, right? Here's test val used as a float. Here's test val used as a float again, right? So I don't really know. And furthermore, I'm assuming I can provoke the error. Nope. So literally, it just doesn't think casting test val to an F32 is a problem right up until the point where you actually assign it, I guess. I have no idea. Like, I can't even hazard a guess as to why that's the case. Good luck, right? So I have no idea what's going on there. I really couldn't tell you. I'm happy to write it this way if it makes people more comfortable, but either way, one should have been fine, and it's just moving that to an integer, from an integer to a float, which is fine. But let's talk about this part here. So if I force it to do this conversion, and you can see that it's complaining about it, which makes perfect sense. If I force it to do the conversion, like so, I just want to show you why this is relevant in some way. So when we actually go and look at what happens here, what you can see in this particular case, right, if I inspect the actual values that we get, like, you know, that the CPU is actually going to use. If I look at each of these things, I don't know. Yeah, there we go. Well, actually, let me do this. So if we were to look at these actual values, what you can do is you can see what they actually each get set to. And what you can see here is the actual mantissa of this thing is going to be, you know, right here, and it's going to be set. It's 24 bits, right? So I think usually, and so it's going to be set in such a way that we can actually directly encode this value without any loss, right? So 40A at the head end of my float is going to perfectly transpose to, right, so the power of the thing, the remainder of a power of 2 is going to be like 1 because the actual power of 2 that I'm trying to raise this thing to presumably is 2, like, right, because I want to write it here. There we go. So I want to write this as something that is raised to a power, and then I want to encode it as 1 point something, right? So what I have to do is I first have to figure out how would I represent 5 as something raised to a power, right? And it's a little hard to read this way because this is like, I don't know exactly how this is choosing to write this out, if that is already in power of 2 in binary form or hexadecimal form. I guess it might be. Although, I don't know. I mean, bear with me here. Let me just write this out. I'm not sure what... I've never actually tried this feature in Remedy, so I don't actually know what it's doing. But if I have an integer, right, and I want to represent 5, and I'm going to put it into a thing, I know that I've got like a 1, a 2, and a 4, you know, and some other things that I can use to represent it. So I'm looking for values here that can add to that, right? So I know I want to set the 1 and I want to set the 4 because 1 plus 4 equals 5, and I don't want to set the 2. So this is what I end up in with my integer. So the encoding for an integer is 101 in binary. And in fact, I don't know, I might be able to get that to be shown in Remedy. I guess not. I guess they don't, I don't know if it has a binary specifier, but that's what this would look like if we actually looked at it in binary, right? So then if I want to look at what the float encoding is going to be, well, the float encoding is the same as like when you look at scientific notation for a number. I'm going to have something like, 5e3 or something, like the, 12 times 10 to the third or whatever, right? It's this kind of notation, but in human form, we always use tens as our base. In floating point form, we use 2s as our base, right? So what we want to do is represent this number as 1 point something, right, times 2 to the something. You know what I'm saying? That's what we're actually trying to represent this as. And the 1 point something is binary, right? It's not 1 point, 2, 3, 4, whatever. It's 1.01101, right? It's a binary floating point number, not a decimal floating point number, right? So if we look at what 5 has to be in this particular circumstance, right? Then what we need to do is create a number that will be like 1 point blah, that when we raise it to some power of 2, it will slide it over into the correct position, right? So this is the number we actually wanted. We want 101 point nothing, right? That's what we're looking for in binary, because we just said that that's what it was. So we would expect to see in the mantissa 1.01 nothing times 2 to the power that will slide this in the correct direction, right? So we want this to go 1, 2 over, right? We want this 2 to the 2, right? And furthermore, that 2 value, as you might expect, that 2 value is encoded in a special way in that upper 8 bits, right? The first bit is the sign bit, and then the other 7 are encoded as like, what is it? It's like 127 is 0, so, or something like this. I don't remember the exact encoding off the top of my head, right? And so if you actually look at what the value is that we got here, right? If you grab this over here, if you look at the actual value that we got, what we would see is, well, A, right, is, again, I wish I could show this in binary, because A is just the hexadecimal encoding of 10, right? Like, it's, it's just, because we've consolidated into hexadecimal, you can't see what it is. We go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So the A is just the hexadecimal encoding of 10, and so I assume what's going on here is that the floating point value as we see it, if you look at how many zeros there are, there's 1, 2, 3, 4, 5, and then the A, right? So this is actually the part of the mantissa starts at that 10. It's going to be 1, 0. And that's totally wrong what I said. That 10 value that's encoded there is encoded in binary, right? So that 10 is going to be the 8 plus the 2, which are set such that we get the 101, I believe. Although, well, that's not actually true, because the 1 is implicit. So actually, that's not true either. I should continue drawing this out. I hate having to do this kind of stuff. It's the stuff I'm horrible at. anyway, let's continue this through, because if it confuses me, it probably confuses plenty of people. So anyway, what I was trying to say there is like, okay, so we got the a value there, right? And the a value, as we know in binary, right, that equals 10 in our language, right? But we need to encode that into binary. So if you look at binary, like I just said before, we've got 1, 2, 4, 8, and some things. We don't need any more to make 10. All we need to do to make a 10 value here is we just need a 2 and an 8, right? We don't need the 1 and the 4 for anything, because it wouldn't really help us at all, right? So we know we've got that value, which happens to be exactly what we want, right? We've got a 1, 0, 1. And furthermore, I guess we have it in the position that we would want. Now, the thing that I don't super understand is why, like, this gets into the, like, I only pop into floating point encodings when I absolutely have to, and so my knowledge of them is just super rusty and bad. But the thing I don't understand is why we didn't only need to encode the 0, 1. I'm not sure why we need to encode this at all, because to my mind, it seems like the mantis is always expected to be 1, and we just need this, and then we slide it up. The 1 shouldn't have had to have been encoded. So I'm not sure why we're seeing that, and honestly, it just confuses me. So we should probably look at the floating point encoding thing and look up why, because it doesn't make sense. I don't quite get it, right? I don't quite get why that would be the case. Like, just being honest, I don't understand. Yeah. So I don't quite get it. I don't know why it looks like that. It's a little confusing to me, because I would have thought that it would have been coded the other way. Particularly floating point encoding. All right, so if we look at single precision float, there's 8 bits of exponent, exactly like we said, and 24 bits of the significand. Let me take a quick look here. So that's a bad part of my memory there. So that explains part of it right away, actually. So I was thinking that the sign bit counted against the exponent. It doesn't. The exponent's 8 bits of it's 8 bits of exponent after the sign bit. So there's 9 bits taken up. So that actually is probably where that extra 1 is coming from, right? So if we look maybe I'm wrong about that too, but we'll just see in a second. So if we look at what this value actually says it is here, address of test float. Can I get a memory window here? There we go. Oops. Can I do this? Yeah. So if we just look at the address of test float there, what you can see is it's like 040A0000, right? Although I guess it maybe is the other way around, because I'm assuming this is going in byte order. So it'd be 0000A040, right? So if we encode what that, or if we decode rather, what that value actually represents there, and I go back to my little drawing board here, right? So if we're looking at what 0000 A0 40, if we look at what this actually decodes to in binary, right, like each of these, and I probably should write these a little further apart. Right? So if we look at what these actually decode to, well, 0, 0 in hexadecimal, right? Each one of these is 4 bits. So this is just like binary all zeros, right? Same thing here. So we know this entire part of the binary number is 0. And how many bits do we have here? Well, this is 8 and this is 8. So the bottom 16 we know are zeros. So now we're looking at this part. We know we start with 4 zeros, right? And then we have A, which, like we said, if we look at what the bits actually are, of like 1, 2, 4, 8, right? Then we know that A wants to encode 10, and so we want to encode a 0 here, a 1 here, a 0 here, and a 1 here. So we're looking at that value. Then we have 4 more zeros. Then we have a 4, so that's just the third one is set. So we have a 0, a 0, a 1, and a 0. And this is the binary number we're actually looking at. Now, if we look at where our exponent actually sits, right? What I said is we have 24 bits of mantissa, but the first one is 1. That means we only have 23 bits, so I should have known even when I said that I was wrong about the sign bit, but either way, right? So if this is 16 bits, and we have 23 total bits of significant to make a 24-bit mantissa with the 1 assumed in the upper place, where would we be? Well, there's 4 more to get to 20, and then 23 is 3 more, so it's 7. 1, 2, 3, 4, 5, 6, 7. Exactly as I thought would be the answer, right? So the 1 happens to be in the right place in just this number 5, which was what was screwing with us. But actually, the 1 is implicit. We're not encoding it. That's part of the exponent, which is here, right? So here is that 5 encoded. It's an implicit 1 followed by a 0 and a 1 and nothing else, right? All the rest of this would have been actual data that we could have used to store actual information of our number, but all the floating point number is, it's the integer you wanted slid down with a 1 at the head, right? So if you want to encode an integer as a floating point value, what's the highest bit that's set? You slide it down till that one is going to go into the implicit slot, which means we'll get rid of it, and all the rest of the bits just go into the significant, right? They go in here, okay? We get the implicit one that would have gone here. That means we can use this for our exponent now. What's our exponent? Well, it's the encoding of how far we had to slide the number down. We know we had to slide it 2 places down, right? So we want to encode the exponent of positive 2. But lo and behold, when we get down here, what we find, and remember the sign bit is also in here, so this guy right here, that's the sign. So obviously it's 0 because, you know, it's not negative, right? I believe that becomes set to 1 when it's negative. So obviously what we need to do here is encode that too, but the problem is this is encoded, the exponent's encoded in a super weird way because they don't want to actually have to, you know, I guess process it the way we might normally think about it. I don't really know why they chose some of the things. You can go read about the history of IEEE floating point standardization. It's pretty interesting, actually. But what you can see here is they range from -126 to 127, right? And it says here that -127 all zeros and 128 all ones are reserved for special numbers, but that means that we start, it's a biased value. It's not 2's complement, right? It's a biased value instead. So 0 means -127, right? Not 0. So unlike 2's complement, we're actually just shifting the range over and then it just goes. So what that means is that if -127 is 0 and we want to encode 2, we need to add 127 and we're going to end up with what? Like 129, right? Is the value we actually need this stuff in here. Make sense? And so how would we encode 129, right? What would we actually do to encode 129? Well, again, remember your binary. I want to encode 129. I have 8 bits to do it. Well, 1, 2, 4, 8, 16, 32, 64, 128. How do I encode 129? Well, thankfully that's a little bit like shooting fish in a barrel because it turns out that 128 is right there. So 1 added to 128 produces my 129. I don't really have to go very far through the list, right? So I know these will all be zeros and this will be a 1 and this will be a 1. And hey, lo and behold, What's sitting right here? Exactly that value. Right? So that's how the actual encoding process works. But what that means, if you look at just literally that little digression that we had there, which I'm really glad we did, because again, like I say, I'm really rusty at some of those sorts of things, and they fall out of my brain. So it helps me to go over them. It helps me as much as it helps you, because now I remember it more solidly, and maybe I won't forget it again for another 5 years or something. All right. So anyway, what we know is that this value has to be something reasonable, right? I can't just shove any old value in here and expect it to work. Because if I make a value that's high enough that it can't represent that number, if it's enough bits to represent the number, right, then it won't work. So let's see what actually happens here. When I write 5, and I set the breakpoint here, what I will see is when we go through what happens to this number, my round trip value will be the same as the value that I put in. So when I look at the test val, and I look at, test val, and I look at the round trip, I get 5 in both cases. And that's because floating point can represent the number 5 exactly, right? Not an issue. However, if I was to put in another number, I might not get that result. Now, you might be thinking, well, I just need to make one big enough, right? So what if I just did one that required 26 bits to represent, right? Surely that won't work, and then when it round trips to float, it'll break. But actually, not true. And what you can see here is when I actually run it, that I should, unless I'm going to be totally embarrassed here and it's not correct, but I should get the same number back, right? And I do. The reason for this is because, remember, we have this arbitrary exponent. So actually, even though it takes 26 bits to represent this number normally, since I have an exponent and there's only one bit set, right? When I go to do this, it just encodes the entire number into the exponent. It just says, oh, it's the exponent's 20, what did I say? The exponent's 26, right? So all it has to do is encode 26 here, nothing here, and it's done, right? So that was very, very simple. It actually isn't hard to represent that. How do I break it? All I've got to do is just stick those bits far enough apart. So this is the real weakness of floating point values compared to integers in this case. Integers can store a number where there's a bit set 31 places away from another bit set, right? A floating point value can only store a number where there's a bit set and then there's 23 places to the next bit set, right? So if I spread out my bits by 26 places, as I have here, or 25 places you might say, or 24, depending on where you count the inside, the outside of me, right? There's a fence posting nomenclature problem there, right? But let's suppose I just spread it out by some number of bits clearly larger than the 23 that I could use. Then when I do it, now I'm in a bit of trouble. And what will happen is I won't get garbage, right? But I'll lose the bits on the end. So that bit that I ored in there, right? You see it? It got lopped off. It can't remember what happened down there, right? And so that's the real weakness of floating point values. And so when you have implicit conversions that go between float and integer, if you're going from the direction integer to float, you have to worry about numbers that are spread apart by more than the number of bits, right? Those numbers will get truncated, and that's the problem. If you're going from floating point to integer, then you have to worry about where the actual decimal point is, because those are the bits that will get truncated, right? If that makes sense. And then the other thing, of course, you have to worry about is if the exponent's really high. Because the exponent's really high, then that number there, it needs to put it in like the 78th bit, but that doesn't exist in integer, right? So again, hopefully that gives you some appreciation for what's going on here and why I don't think it would be any problem to just put a 1 here, because when that converts to floating point, it's exact, and there isn't a difference really between writing a 1 and a 1.0f in this particular case, I don't think. Why the compiler is choosing to output the warnings that it's outputting, I don't really know. That seemed a little bit weird to me, and so I really couldn't tell you why it shows the warnings it did. Hopefully that helps. Let's go again. Hopefully that's enough of a digression into there. And for asking what debugger it is, it's Remedy. It's this debugger. It's $20. It's, you know, for all intents and purposes, these days for me, it's has all the features I actually need. There's some features that Visual Studio has that it doesn't have. But it basically meets my needs, and it is way better to use than Visual Studio. All of the crap about Visual Studio is gone, and you know, even just basic stuff like, you know, if you come in here and you look at like the light, like this light probe index thing, right? So one thing that you'll notice happens in Visual Studio these days, it just absolutely drives me insane, is like when you actually run the program, the watch window doesn't update for like a few seconds half the time. Here, you can just wail on the F5 key and look, like the number goes up. Like that's actually usable. I can just watch if I wanted to get to one, I could stop on the one I wanted, you know, it's just like, it's actually usable again. It's one executable, no installer. You just put it on your machine and run it. It saves your window layout, doesn't all get all screwed up all the time. It's nice and fast. It boots instantly. You don't have to wait. There's no splash screen. And so for me, it's just like, for $20, it's like the best $20 you'll ever spend if you debug programs. Yes, once in a while, if you need some specific feature, like downloading stuff from Microsoft Symbol Server or something, you might have to switch back to Visual Studio Debugger that day. But for everything else, you can pretty much just use this. And I really haven't had much problems with it. And new features are coming, so someday maybe I won't even have to add that caveat. It'll just be good enough that there's no reason to ever switch to Visual Studio. Because honestly, Visual Studio is not that good of a debugger. It's not as good as WinDBG. It has a small subset of the features of WinDBG, right? So, have you tried Clion? Its debugger is awesome. Somehow I doubt that, but no, I haven't. What's Clion? So, like, here's what I'll say. I can pretty much guarantee you this debugger isn't awesome. Like, the chances that this is awesome seem so low to me, but maybe it is. I don't know. I don't know how to, like, see, is there like a, is there a way to actually, like, man, I guess I can search for certain things and see. So I'm assuming, I mean, can you see the assembly at the same time that you can see the regular source? I mean, unless I'm mistaken, isn't this saying that you can't even look at the disassembly of your own code? Wonder if I I feel like I tried this on Linux one time. Like, did this actually ever get implemented? I mean, yeah, like, okay, so, and what about like the register view? What does that look like? Does it even have one? I mean, okay, so just to be clear, like, I could try it sometime on stream just as an entertainment exercise, I suppose. But, like, if you can't step through assembly language as part of your daily process automatically in your own code with source highlighted at the same time, and you can't have a register window, then this is not a serious debugger, right? This is, I mean, I wouldn't even start trying it if it can't do those things. And my assumption, I think I tried this because I remember trying a bunch of debuggers on Linux trying to find one that was any good. I think I tried that one, and I remember it being so slow as to be almost like unusable anyway. So I'm guessing that, like, no. I'm guessing this debugger is so far from awesome that it would not even be, it would not even get the A in awesome, let alone the final E. I mean, it definitely would not be a replacement for Remedy if it can't even show, like, assembly language as I'm debugging, right? Because that's, like, critical. I don't want my assembly view to be only when it can't find the source code, because assembly is critical to see all the time. Like, I look at it every couple of days, right? Sometimes all day I'm looking at just the assembly. All right, let's go ahead and wind down. It's a long stream today. Thank you everyone for joining me for this one of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org. Comes with the source code so you can play around with it. You got all week to put the lighting in, actually. If you want to start playing around with the lighting, we just started the probe stuff. I'll be back here next weekend, probably, I think. Hopefully, I'm assuming. I'll be back here next week to work on getting that lighting stuff implemented fully. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.